First of all, this was said over and over again, but I would also like to thank the organizers for letting this conference happen. It was an unbelievable experience to be here, so thank you for that. So let me first, well, I'm Henry Lopez. I'm working in the group of Matthias Weidemüller, and we're collaborating with Roland Wester from the University of Innsbruck. So let me just begin with a little motivation why we are doing this whole work we are doing. So I'm pretty sure I don't have to convince you that cooling of matter is of fundamental meaning in physics. Yeah. So because this allows us to study the quantum nature of matter, and laser cooling has been for this aim. Being the working horse of cold physics. With laser cooling, you can cool down atoms to a Bose-Einstein condensate, or make these fancy ion crystals, and even molecules have been cooled with laser cooling. But if this working horse fails, then you have to seek for alternatives. And one of these alternatives is sympathetic cooling. Where you take just one species that is already cooled and take this as a refrigerator for other species that cannot be laser cooled. There is where hybrid systems come into play. This is just, in the pictures you see just 3 examples of these hybrid systems that have been built out around the world. Yesterday we saw these beautiful presentations by Eric Hudson and Professor Asiri. But now in this field, what remains very, very unstudied are anions. So all the studies we have been searching or looking at until now are for positive ions. But anions are completely unstudied in the ultra-cold regime. To my knowledge, anions, or the lowest temperature an anion has been achieved, is about 5 Kelvin, which is limited by the coldest buffer gas you can take out of a bottle, namely helium at 5 Kelvin. There is where we come into the game, so to say. We choose OH minus. Not only because it is a very important anion, you can find it everywhere, but it's also very well known, and this makes OH minus a perfect system if you want to do new studies in the ultra cold regime. As a buffer gas, we choose rubidium. This has some advantages, but it has the main disadvantage that the mass ratio is 5. And I remember when I was the first time as a PhD student in a summer school presenting this poster, people were telling me, "Hey, Henry, you're crazy. You're not going to be able to cool your ion by such a mass ratio. Everybody knows that you're not going to cool it down." So this is the story I wanted to tell you today, namely sympathetic cooling of OH minus by a heavy buffer gas. Today I'm going to talk to you about a little bit of the function of Paul traps. This we have been seeing already during this conference, but I want to tell you what's the difference between these Paul traps and the multiple radio frequency traps. And then we are going to put into this system some atoms and let them interact with the ions and see what happens and in which extent we can sympathetically cool the ions. After that, we're going to talk about a little bit of force hybrid system, and we are going to see what's the strategy and what's the latest results or the status of our experiment. After that, some concluding remarks, so let's begin. This is the typical picture you get from a Paul trap. Here you have the radio frequency electrodes where you apply the radio frequency voltage, And if you put an ion inside this trap, this is the typical trajectory you're going to see inside this trap. This is very well understood. As stated yesterday already, you can divide now. If you look at the position of the ion as a function of time, you can divide this motion that the ion is making inside this trap into two motions. Mainly this big oscillation called the macro motion, and this wiggling we see here and here called micro motion. The main difference between these pole traps and the multiple traps, in this case for an 8-pole trap, so meaning we have a trap order of 4, is that the micro motion has disappeared in some regions of the trap, namely when the ion is achieving the trap center. Yeah? And for the micro motion, you can describe this motion as the ion being in an effective potential. So for a pole trap, you see this harmonic potential, but as you increase the pole order, you see that this effective potential gets flattened in the middle of the trap. Yeah? And you can say that the macro motion can be expressed as a motion in these effective potentials. So now, what happens if we put in these traps an atom? Here again, the position of the ion is a function of time, and we put now an atom with 0 velocity. It's at rest, and just for these examples, we're going to take the mass ratio of 1. And now, this has already been explained yesterday, but here again, if the collision happens now in the middle of the trap, the collision is going to take to make what you would expect from any elastic collision and energy conservation. If the atom is not moving and the ion is colliding with it, the ion is going to lose energy. Yeah? But the non-intuitive part of this dynamics is, even if the atom is not moving at all and it collides in the outer part of the trap, because of this micromotion, the ion is going to gain energy. And the point is here, whether the ion gains or loses energy depends on where the collision has happened. So now we can do some Monte Carlo simulations, roll the dice for different impact parameters and so on. And this is exactly what we saw before. We see here the relative energy change before and after a collision for a given energy of the ion. Negative relative energy change would mean that the ion has lost its energy, whereas here in the outer part of the trap, the ion is going to gain energy. So small collisions readily lead to an energy loss. This was for the case for a mass ratio of 1. So let's keep these and let's compare what happens if the mass ratio now decreases or increases. Now this heating effect here, if you have a very high mass ratio, this heating effect is going to be everywhere inside this trap. So large mass ratios lead to an energy increase of the ions within these systems. So let's keep this case, because we have this mass ratio, and now compare with what happens if we now increase the number of poles we have in our system. And you see here already that in the middle of the trap, if you have a higher pole order, in the middle of the trap, the ion is going to make this elastic collision. It's going to lose its energy. Because here in the middle of the trap, the macromotion has disappeared. So Now, what we can do now is, well, let's keep this example of a Powell trap and small mass ratios, and fill out our trap with a buffer gas. Now, the buffer gas has a finite temperature, and roll the dice. And what we can do now is calculate the probability distribution of the ions, the final probability distributions of the ions. In this graph, it's a log-log plot. The red line would be the thermal distribution of the ions. So this is the Maxwell-Boltzmann distribution in a log-log plot. And the points are the simulated final probabilities for the ions. And what you see here is that now if you increase the mass ratio, these power laws emerges. So non-thermal distributions are emerging. And yeah, as already said yesterday, a lot of people have been thinking about this. And they came out with very similar results, claiming that there is a critical mass ratio where these energy distributions still stable. So the mean of this energy, where the mean of these energy distributions diverges. Yeah. So the main point here is that we can now do our simulations for different trap orders. And the main point here is that the critical mass ratio becomes pole order dependent. So it scales linearly with the pole order. So for our case, we have a pole order in our trap. We have an A-pole trap. So we have pole order of or trap order 4, meaning that our critical mass ratio would be 4 or something like that. And we're still not there. But what we can do is just confine our buffer gas, because yeah, we have a mod, and we can very well control the size of this beam. And what happens now is that if the probability distribution, if you make again these calculations, these events where the ion has gained a lot of energy are just cut. So this power law get cut, and we get again stable probability distributions. You can make this further and decrease the sigma of the atom cloud. And what happens is that if you do that, the ion energy distributions are pushed into lower energies. So localizing the buffer gas improves cooling. And this is an effect what we call forced sympathetic cooling, because you can now, if your ion cloud reaches a steady state, you can just decrease the size of the atom cloud and further cool down. So there are a lot of details that I haven't told today, but you can read this on these papers. So let's talk now about our hybrid trap. As I already said, we have an A-pole radio frequency trap combined with a special kind of magneto-optical trap. It's a dark spot. So the hybrid trap setup consists on two main chambers. This chamber is dedicated to create our ions or negative ions, and to accelerate them towards the trap. And here's where we combine both of the traps. This is a picture of how it looks like in reality. So for axial confinement, we use hollow end cap electrodes, and for radial confinement, we use very tiny, very thin radio frequency wires in order to get optical access into this, because we want to make a mod inside this. So we create our ions, we trap them, and what we can do now is to let them interact with a buffer gas, filling out our whole trap. or turn on the cooling lasers and make the ions interact with the rubidium cloud. And then the only way we have to see what happened with the ions is to detect them with an ion detector, because we cannot let them fluorescence because they are negative ions, and yeah, you can just not see them. So the way we do, the way we want to measure the final temperature of our ions is via two different methods. The first one is photodetachment tomography, and the second one time of flight. And in the first case, via photodetachment tomography, the strategy is following. If we were able to measure the ion's spatial distribution and know the potential landscape, then we can fit the final temperature of the ions. So for the ion spatial distribution, we make use of a destructive method. We let the ions interact with a photodetachment laser that is able to detach the electron out of our ion. And how fast this process happens will depend on, of course, the wavelength of your laser and the internal temperature of the atoms. So the point here is that we now choose our wavelength of our atoms of our photodetachment laser such that it doesn't depend on the inner temperature of our atoms, of our ions. Okay, now you can model this process, so to say, within a very basic rate equation, and what comes out is very astonishing, actually, because you can if you measure the decay rate of this process as a function of the laser position, where your laser position was, and you know the experimental parameters, the power of the laser, the frequency of your laser, and the photodetachment cross-section, then you come out with a normalized column density of the ions. So we did this in this region marked here, and these are the results we get. So color-coded, red is a high density of the ion cloud, and blue is where, well, no ions has been lost. This black region we cannot scan because the radio frequency roads are in between. So with this method we were able to measure the ion's spatial distribution of our cloud. So we have made a picture of ions that you cannot see, which is very, very impressive, actually. So this we keep in mind, and now we take a look at the potential landscapes. For this, we rely on a program that is called SymIon. So we load the whole electrodes we have in our trap, and we let it calculate the potential landscape. And this is a typical picture of what you get from a potential landscape inside this trap. So now we know the potential landscape, and we can put some energy distribution in this potential landscape of the ions, and calculate how it should look like. And if you compare us now simulations and measurements, you see a very good agreement. The simulations are doing a very good job, but we still see that the translational temperature we fit is not as we would expect, because for these measurements we were doing the ions have interact with a buffer gas at 300 Kelvin, helium at 300 Kelvin. So we are kind of puzzled why the ions are not thermalizing with a cloud, with a buffer gas cloud. So this is the first measurement we can do. But the second measurement we can do is via time of flight. And okay, for this aim, we also rely on SIM ion. Here we model again the radio frequency drop, the whole ion optics in order to guide them into the detector. Here we have a field-free region, and after that, the detector itself. And now what we do is we initialize an energy distribution. We let the ions have a certain temperature. We modulate or simulate the trajectories of our ions here in blue, and we track the time the ions has arrived to the detector, and this is the first simulation. So we histogrammize the ions where they have been arriving to the detector, and what you see is that as you decrease the temperature of your ions, also the time of flight distribution shrinks, and this is actually very surprising, so to say. Well, now you can just fit a normal distribution within these distributions and plot the width of these distributions as a function of the temperature of the ions. And what we have seen is that this correlation behavior doesn't depend on how you extract the ions. So, I mean, if you make, for example, a steeper extraction potential, of course, the width of the time of flight will change, but these behavior potentials are relative to a certain temperature is going to remain exactly the same, with small deviations, but still exactly the same. So we keep that in mind, and now we do experiments. Yeah, and the way we do that is well, we have our ion cloud. We let it interact with our ions, the ions are interacting with the buffer gas, with the MOT. We extract the ions and count them as single ions. So we record now the time the ions have arrived to the detector, and the single ion we do because we need enough time resolution for the time of flight experiments. And now, this is the first time of flight distribution for the anions having interacted with helium buffer gas at 300 Kelvin, and now we turn on the MOT, and this is what happens. So after 500 milliseconds of interaction time, not much had happened, because in this time the mode was loading, but already after 1 and 1.5 seconds, you see that clearly the ion distribution has shrinked. So by these results, we're already pretty sure that our ions has been cooled by the MOT. We can play again the same thing, just fit a normal distribution within these time of flight potentials, time of flight distributions, and plot the sigma of the time of flight as a function of the interaction time. And you see here a little bit more clearly that yeah, the sigma is decreasing by a factor of about 25%. And yeah, we were pretty happy about these first results, because, as I said before, nobody or almost nobody believed that this experiment would ever work. But it did, and well, we can now make a little estimation. So we know that the ion this time of flight distribution has a strength in 25%. So if we take a look again at the simulations, we end up with a temperature of 150 Kelvin, which is not the dream temperature we want to achieve. I think we can go further down. For example, by applying this forced sympathetic cooling I explained you at the very beginning. And yeah, but I mean, for these measurements, we were limited by inelastic collisions. These we can control in a certain way, and so we believe that we can go further down in the temperature. So with this, I would like to summarize my talk, or the take-home message is that sympathetic cooling inside a radio frequency trap is indeed possible even at large mass ratios. We have measured the temperature by two different methods, namely photo detachment and time of flight. And yeah, the most important message is that sympathetic cooling of anions has been verified experimentally, and we want to go further for sympathetic cooling. The outlook of our experiment is, I think, very rich, because yeah, we want to do internal sympathetic cooling of OH minus. It turns out, in a recent paper by Gonzalez Sanchez in the group of John Turco and Roland Vesta, they have seen that OH minus and rubidium, in that system, OH minus can be de-excited in its internal states. That means that with our experiment, we should be able to cool down our OH minus internally and externally in a single shot, which would be very nice. The second part is, of course, a little bit of chemistry. There has been a long-standing discussion about this system, OH minus and rubidium. Johannes Deigelmeier, already a couple of years ago, in the group of Matthias Weidemüller, in a similar experiment, were able to measure these cross sections for OH minus and rubidium, and a follow-up paper by Robert Coté from in this paper has claimed that OH minus and rubidium shouldn't react, at least not at the ground state, as we have in our experiment. But a follow-up paper by Milan Kas in Brussels has shown that it is indeed possible that that this reaction is taking place. So by a further measurement with a certain more control of this system, we should be able to now measure the cross sections and challenge again the theoreticians. And as a last thing we want to do as a long-term goal in this experiment is the study of water clusters. Those are water molecules that are attached somehow to OH minus, and about these clusters is virtually nothing known. And we hope that by letting them interact, we also could cool down these kind of molecules and look at the internal structure of these anions. Yeah, with this I would like to thank you everybody, and to thank all the team working with me, my boss Matthias Maybmüller, our collaborator Roland Vesta. A special thanks should go to Bastian Holkemeyer and Jonas Tauch, there are people who has been working with me in the past few years, and yeah, thank you very much for your attention.
There is time for questions. Any questions? Yes.
So with this OH minus water, you plan infrared spectroscopy, or how do you?
Yeah, like with water clusters, you mean? Yeah, well, as I said, virtually nothing is known about these water clusters, and yes, what we want to do is spectroscopy on them, and yeah, there are certain ideas we have to in order to investigate the structure of these water molecules, but yeah, as I said, it's kind of a long-term project we have. Yeah.
Would you produce rubidium OH minus by radiative association? Or?
Yes, exactly. So I didn't go into details to this, but what you produce if you let these two particles collide is well, there are three reactive channels. This is the one of them is these molecules making rubidium hydroxide. It could but also happen that OH minus make charge transfer to rubidium, and yeah, you can calculate this within this picture the crossing point of this reaction, and yeah, make certain estimations how the system is going to work.
And experimentally, you think you can measure this cross section?
Yeah. We are going to, exactly. So this is not like the experimentally determine or measure the cross sections of OH minus and rubidium is not a big challenge, I would say. So you just have to measure the decay rate in as a function of the bright state fraction of rubidium, and then yeah.
How big is N there in the cluster?
You can have, well, we have seen in our experiment, we have already seen water clusters of about, yeah, N equals 6, I think, but you can go longer than that, yeah. These we have to optimize in the experiment, but yeah, you can get very, very big anions, yeah.
Good questions, yes.
Do you expect to see the RBOH molecule in your system?
Well, not directly. I mean, you cannot separate different reaction channels because you just lost your anion, and then you could speculate what happened with the system. What we could do eventually, that would be hard, but we are thinking about doing that, is the reaction channel of OH minus giving its electron to rubidium. I think, yeah, this could be measurable because then we have again a negative charge that is trapped at our ion trap directly. The hope is that we can detect it, but the problem is then the Mott lasers, that they are going to detach the electron out of rubidium instantaneously, so to say. So, but yeah.
Other questions? No, there are no other questions. Let's thank Harry again.